Okay, in this lesson we're going to be using information from an experiment, a calorimetry experiment, and we're going to take that information from the surroundings and use it to calculate the enthalpy, or delta H, for the system. And so due to the fact that we cannot actually see what's happening in a chemical reaction, and we cannot actually see what's happening on a bond-by-bond basis, we need to do an experiment so that we can get information about the surroundings and transfer that to the system. So the general principle to this is based on the conservation of energy, the law of conservation of energy. And it states that if our surroundings, right, we learned about calorimetry the other day, if our surroundings loses or gains heat, it means that our system has done the opposite. So if I'm breaking this equation into two pieces, I can think of the Q as being what's happening to the surroundings and the delta H as what's happening to the system. And we also learned yesterday about molar enthalpy, and that's enthalpy on a per mole basis. And so if I take that total enthalpy and I break apart the moles, I can get the molar enthalpy. So this delta Hx here is what we call the molar enthalpy. And so if I divide off the moles, I can get what the enthalpy change is of the system on a per mole basis. And the other half of this equation is just our equation that determines the properties of the surroundings. That's the mass of the surroundings, the heat capacity of the surroundings, and the change in temperature, just like we learned about in calorimetry. All right? And I guess maybe just to complete this, remember Q equals mc delta T. That's how we dealt with the surroundings. In this case, the total delta H is equal to the molar enthalpy times the number of moles, and that gets us this half. All right? So depending on whether we want the total enthalpy or the molar enthalpy, that'll determine which equation we want to use here. And in this case, this is the heat, and if we want to figure out what that heat is, we can use this equation here. Now, when we do calculations like this, we need to assume a few things. We need to assume that our calorimeter doesn't lose any energy. And when we look at assumptions, essentially we're talking about possible errors. If we're trying to minimize the errors in an experiment like this, then we're going to try to minimize the heat that actually gets transferred to the surroundings. And you can't stop that, right? If you have something that's hot, let's say you got a cup of coffee here, and that cup of coffee here is hot, all right? Then eventually that heat is going to leave into the surroundings. There's nothing you can do, and it's going to cool down and become the same temperature. So our assumption is that no heat is transferred, but we know that there's always some heat transferred. So that's a possible error. Any heat that exchanged with the calorimeter and the material is negligible. So again, this is kind of a restatement of number 2. It means we're assuming that our calorimeters are pretty good at holding in the heat. And the last assumption that we need to make has to do with the mass of the surroundings. Now, the surroundings for our experiments are going to normally be water. We're going to have the heat transferred into that water. But if we're doing a chemical reaction, sometimes we're not going to be dealing with water, but we're going to be dealing with dilute aqueous solutions, like maybe some weak hydrochloric acid. Now, if we're dealing with dilute aqueous solutions, it means that we're not dealing with pure water anymore. And so it turns out that the density of that aqueous solution may not be exactly equal to 1 gram per milliliter as pure water is. But we're going to need this conversion factor to convert any volumes into grams so that we can put those grams into the surrounding mass. So our assumption here is that any dilute aqueous solution that we're dealing with is going to have the same density as water. All right? We also need to use the heat capacity of water. We've already seen that. It's 4.18 joules per gram degree Celsius. And again, if I'm dealing with a chemical reaction and that chemical is a dilute aqueous solution, then its heat capacity is not going to be exactly the same as what pure water has for its heat capacity, and therefore it won't be exactly 4.18. But there's no way to calculate what exactly it is, So we have to make an assumption that it is 4.18. And again, each of these assumptions, while doing an actual experiment and doing our calculations, are sources of error. They are places where our answer in a real situation will be different than our calculated answers because of these assumptions. Let's do some example problems. Okay, so this is for physical changes. So we're talking about dissolving, freezing, or melting, or boiling. And so it's asking us here to determine the heat of solution, the delta H solution, which means dissolving, of potassium chloride, given that the temperature of 100 milliliters of water changes from 24.1 degrees Celsius to 20.0 degrees Celsius when 7.46 grams of the potassium chloride is dissolved. So in this first statement, you'll notice we've got the subscript, which means we're looking for the molar enthalpy. Our equation for determining what the system is doing is delta H equals negative Q. And you'll notice because we want the molar enthalpy, we're going to use N delta HX. In this case, the X is dissolving, but we can leave it as an X in the equation. And because we're given some water and some temperature changes, we're going to need MC delta T. All right? Now to just gather up our information, I want to break my page into the two halves. This side here is our system, and this side here is our surroundings. So let's gather up our information that way. So we've got some KCl and it's dissolving, and it's in some water. And so this water is going to heat up. And remember, the purpose of the water is to gather up the heat and have its temperature change. This water is our surroundings that is gathering energy up. So the M, all right, now notice we have 100 milliliters, but we know that the density of water is 1 gram per 1 milliliter, so we actually have 100 grams. More surroundings information. Well, we know it's water, so we know the C is 4.18 joules per gram degree Celsius. And delta T, that's the change in temperature, and we could calculate that even before we put it in the equation, T2 minus T1, and that is going to be equal to, what are our numbers here? The temperature is dropping, so T2 is 20 degrees Celsius, and T1 was 24.1 degrees Celsius. So in this case, the temperature dropped, and that's okay. That means we're going to have a drop in temperature of, and what do we get here for our drop? It looks like negative 4.1 degrees Celsius. Back to our system. We need some moles because we want to solve for the delta HX. So what is our system? Our system is potassium chloride, and it is dissolving. The question is, how much potassium chloride? And we're told here in grams that we have 7.46 grams of potassium chloride. Pardon me, Cl. All right? Well, in order to complete this side, I can't put grams in there. I need moles. 7.46 grams times, I need the molar mass of potassium chloride, 35.5, potassium 39.1, 39.1, and when I add those together, I get 74.6 grams per mole, and so 1 mole is 74.6 grams, and if I divide that off, I get 0.1, and for significant digits, 0.0 moles. Okay, so I've got moles, I've got MC delta T, I should be able to solve for the delta HX. So I'll rewrite N delta HX equals negative MC delta T, 0.100 moles, delta HX, pardon the scribbles, M 100 grams. Oh, I dropped the negative. Negative. Put brackets around the mass. C 4.18. Delta T negative 4.1 degrees Celsius. Dividing off, right? So now if I divide off my 0.100 and divide off my 0.100, I'm going to end up with a delta HX, a molar enthalpy, and when I run that through my calculator, I get 17138 joules per mole. All right, 3 significant digits. If I were to convert that into scientific notation, 1.7138 times 10 to the 4 joules per mole. And if I were to round then to 3 significant digits, 1.71 times 10 to the 4 joules per mole. All right? Okay, so we analyze what the system is. In this case, it was potassium chloride dissolving. We analyze our surroundings, water being cooled down in this case. Note here that the sign on our delta HX is positive, and positive means it's endothermic. It took energy in. And when something is endothermic, it tends to get cold. And as you can see up here, our temperature dropped, which means it got cold. So that was an endothermic reaction when the potassium chloride dissolved. It resulted in a positive delta HX. Okay, let's look at number 2. Again, we're talking about physical changes. Again, we're dissolving some lithium chloride, and this time we're looking for a mass of lithium chloride. And we're given the molar enthalpy of dissolving for lithium chloride, negative 37 kilojoules per mole. All right? And we want to find the mass. Again, we're dissolving it in some water, so we've got a temperature change, and we've got a mass. And so again, because we are given a molar enthalpy, then we're going to be using our N. So we'll jump straight to this. N delta HX. In this case, it's a heat of solution. So we're given that information. And we obviously have some water information, negative MC delta T. Again, just like before, let's gather up our information. This is the surroundings. This is the system. So in this case, what mass of lithium chloride? The lithium chloride, right? Mass of lithium chloride, that's what we want to find. Now, in our equation, now obviously the lithium chloride dissolving is the system. It's what's doing something chemically. The surroundings are the water. How does the water change in temperature? So the mass of our lithium chloride is what we want to find. And we don't have mass in our equation, but we've got moles, so we can easily get that from that. And we know the delta HX. That's been told to us. Delta H of solution, I'm just going to write it as delta HX, negative 37. Now notice, it says kilojoules per mole. Now in our equation here, C is always in joules, which means I need to convert this thing over to joules, negative, the problem. We've learned in the past that kilo is times 10 to the 3, and that is joules per mole. So now we've got our delta H in joules, which is what we need. Let's get our surroundings information. Mass of the surroundings. Now that's mass of water. That's the water that we are dissolving it in. And it says here what mass of lithium chloride at the temperature of 200 grams of water. So there's our mass there, 200 grams. No need for the density this time because we were given it in grams. And the temperature change, we're told the temperature increased by 8.5. So in this case, we don't need T2 and T1. We have a temperature change of plus 8.5 degrees Celsius. All right? C, we know that as 4.18. Again, joules per gram degree Celsius. So that's why I needed to convert this guy into joules, because this guy is in joules. So the unknown here is moles, and once we get moles, we can get the mass. So N delta Hx equals negative mc delta T. So N, and then this is negative 37 times 10 to the 3 joules per mole, negative, and the mass 200 grams, the C 4.18, the delta T, in this case, positive 8.5 degrees Celsius. Notice the two negatives will cancel each other out. In order to complete this, I'm just going to divide off 37 times 10 to the 3, divide off 37 times 10 to the 3, and again, the negatives also cancel, right? So that negative 1 cancels that negative 1. So when I calculate that out and I run it through my calculator, I get 0.192 moles of lithium chloride. All right? Okay. And the molar mass of lithium chloride, LiCl, 35.5. Lithium is 6.9. That gets me 42.4 grams per mole. And therefore the mass will be 0.192 moles. And we know how to do this. This is good old-fashioned conversion factors, and that is going to be 42.4 grams per 1 mole. Okay, and I get a number of 8.14 grams. Okay, and there are some practice problems. You've already been given the calorimetry worksheet, and there is a textbook reference. Let's now talk about some examples that involve chemical change. The last two examples we did involved dissolving, which is a physical change. Now let's talk about what happens when we deal with some chemical reactions. There is really no difference. The only difference is, again, we'll be dealing with solutions, so we've got to use our assumptions. The fact that that the density of the dilute solution is the same as the density of water. That's our first assumption. And the second assumption is that the heat capacity for our dilute solutions is the same as the heat capacity for pure water. They actually aren't, but that's what we have to do sometimes in order to solve a problem. We have to make some assumptions. Okay, so like I said, there's not much of a difference, except we're going to be dealing with a chemical reaction. Now, we really don't need to worry about this chemical reaction when doing these calculations in this case, because we want to solve for the molar enthalpy for a particular reactant. You'll notice there'll be a particular reactant that is going to be referenced, and that's going to tell us what our system is, all right? The system is the entire chemical reaction, but when we do a calculation, we need to define it in terms of one of the reactants. So we have 50 milliliters of 0.3 molar copper sulfate reacted with 50 milliliters of 0.6 molar sodium hydroxide in a coffee cup calorimeter. So we're mixing two solutions together, all right? Both solutions start at room temperature, so we both have a T1, and we are waiting until they reach that highest temperature, and they result in a highest temperature of 24.6 degrees Celsius. Now, this is not the same question as mixing hot water with cold water. It is actually a completely different question. We are mixing two solutions that start at the same temperature. A chemical reaction produces some energy, and the temperature of the solution increases. We actually end up with one solution at the end because we have to combine our two solutions into the same reaction vessel. So just like before, all right, we're going to need to think about our system and our surroundings. So here we're going to have, again, N delta Hx, our system, and negative mc delta T, our surroundings. We're looking for a molar enthalpy, so again, I'm looking for the delta H subscript X. And we're looking for it in terms of copper sulfate, which allows us to focus in on what we need, because we're going to need moles. And we have two numbers that can supply us with moles: the information about the copper sulfate and the information about the sodium hydroxide. So two reactants. But in the question, we are asked to do the question in terms of copper sulfate. So I need moles of copper sulfate, CuSO4. All right? Now notice we have a copper sulfate solution with a concentration. That means we can determine what that is. 50 milliliters times, and sorry that I'm tight for space, but remember molarity is 0.300 moles per 1 liter. My liters cancel out, and I will be left with millimoles. All right? And we can work with millimoles. We just have to be careful and convert it at the end. So 50 times 0.3 is 15. That's millimoles. And we do need it in moles, so we can bring in our 15 times 10 to the -3 moles. All right? So we've got our moles. We want to find a delta HX. Let's go to our system side, M. Now, this, remember, is the mass of the water. It's the water in which the heat is being absorbed by. We have 50 milliliters from one solution and 50 milliliters from the other solution, and therefore we have 100 milliliters, and our assumption is that 1 gram is 1 milliliter. That's our density assumption, and therefore we can say we have 100 grams of water. Okay, so we add our volumes up. We assume that it's got a density of 1. We have 100 grams of water. C, again, because they're solutions, we have to assume that the C is 4.18, again, joules per gram degree Celsius. And delta T, again, we have two temperatures for this one, T2 minus T1. In this case, it's heating up, 24.6 minus 21.4, and that gets me a difference of 3.2 degrees Celsius. So again, just like before, the only thing missing here is the delta HX. Let's substitute and go. Now, in the previous examples, I've rewrote, but I'm going to just go straight to the numbers here. 15 times 10 to the -3 moles. Delta HX, find. Negative, the mass, 100 grams. C, 4.18. Delta T, in this case it heated up, so it's positive 3.2. I don't have enough room to rearrange, but if you divide this guy off on this side, we're going to get a delta HX. That is going to be, notice, can't cancel out that negative. Negative, and that is going to be, I'm going to check my number, 89173 joules, all right, which is the same as, and again, if we go to scientific notation, we'll be dealing with negative 8.9173, and that again is in times 10 to the 4 joules, and in scientific notation, that is going to be negative 8 significant digits, 392 times 10 to the 4 joules. Also very important to put that into kilojoules, because very often our numbers are in kilojoules, and if I move that 3 steps, 1, 2, 3, that is negative 89.2 kilojoules of energy. Okay? Sorry, and this is per mole. Per mole, per mole, and the last one here, per mole. And that's because we divided off those moles right there. All right? So we didn't do anything differently. The only thing is we had to be told which of the reactants we were going to be working in terms of, in this case the copper sulfate. That allowed us to determine the moles, which then allowed us to calculate the molar enthalpy. And let's do one more. Again, very similar situation, chemical reaction. This time we're reacting some mass of magnesium in a solution. Temperature of the solution is going up. Determine the molar enthalpy for Mg. I'm very tight on space, but I'll see if I can squeeze it in. Again, N delta Hx equals negative MC delta T. And again, let's break it into system and surroundings. And in this case, it says determine the molar enthalpy for magnesium. So I need moles of magnesium as my system. In this case, I was given mass of magnesium, so I'll use 0.50 grams times. I need a molar mass of magnesium. That molar mass of magnesium is 24.3 grams per mole. And this is going to then be 1 mole over 24.3 grams. And that gets me 0.0206 moles. On to the surroundings. Well, M of the water. Remember, that's the stuff that's catching the heat. In this case, I have 100 milliliters of the acid, and it's not pure acid. It's a solution, which means that 100 milliliters of the acid is going to supply us with our water. We need to make the assumption that it is a density of 1, so we have 100 grams of water, C 4.18. Again, an assumption, delta T, T2 minus T1. It heated up to 40.7 degrees, minus, started at 20.4, and that gives us a delta T of 20.3 degrees Celsius. So again, substituting in, again we're solving for the delta Hx. 0.0206 is the moles. Delta Hx, negative 100, 4.18. Delta T, 20.3 degrees Celsius. Again, I'm running out of room, but we're going to divide off the moles to make a molar enthalpy. And the molar enthalpy ends up being negative 4.11912 joules per mole. Now, the last examples I didn't do this, but it is important. We very often will deal with kilojoules. To go from joules to kilojoules, you need to divide by 1,000. So that's a three-stepper. 1, 2, 3. So in terms of kilojoules, it's negative 411.9. We won't worry about the last digits. That's kilojoules per mole. And now we're going to round it to our, looks like 2 significant digits here. So in this case, it's going to be negative 410 kilojoules to 2 significant digits, kilojoules per mole. Okay? So as I stated, when doing these types of calculations for chemical reactions, they really are no different than if we're doing them for a physical change. We need to be told with respect to what that we're doing our calculations to, which of the reactants. Once we're told that, we can then find the moles of that particular reactant, which then allows us to get the molar enthalpy in terms of that particular reactant. Okay? All right? So, again, there are some practice problems on the calorimetry worksheet, and you can work through those.